I'm recording another video for 113. Last time we started a new topic, the universal gravitational force discovered by Newton. And he also discovered the equation to calculate the force, which is this equation. And the big G is a constant, very small number in SI units. And then we also compare this universal equation to the equation we have been using to calculate the gravitational force from the Earth on us. And then we figured that this is actually a conclusion from the universal equation. But if this is a universal equation, this must be true for any two objects. So it's also going to be true between any object and the Earth. And then if you apply that equation between the object and the Earth, then you can't ignore the size of the Earth. So the distance you use, this little r is always a distance, but sometimes it will become a radius in the problem. In this case, you're going to plug in the radius of the Earth because you're going to use the distance from the center of this Earth to this object. And then when you factor out this mass of this object, you will get a factor, big G times the mass of the Earth divided by the radius of the Earth as well. And then if you have applied this conclusion to any object on the surface of the Earth, you always get m times this factor. So why don't we just call it, and this is going to be a constant, right? Because all these three numbers are constant. Then why don't we just call this guy another constant, so whenever we calculate the force of gravity from the Earth on any object on the surface, I'm just going to do mass times this constant, and this constant is the free fall acceleration, right? So this equation is actually a shortcut equation from the general equation, and then this is going to be how you calculate this little g free fall acceleration using this the mass of the planet or star and the radius of the planet or star. And this is going to be a general conclusion for any planet or star, right? Because you can always do the same math, and then you always get little g is going to be this. And then once you find the little g on the planet or star on the surface, then you can go ahead and use this shortcut equation to calculate the force of gravity, right? So now let's practice this equation. So this is a conclusion. So everything in this part can be derived from this. So that's what we're doing, right? This is a conclusion from, if you compare these two equations. Again, this is not something I need to memorize. Once you understand the difference between these two equations, it's very easy for you to figure this out, okay? Now let's apply that to the surface of the sun, okay? So this is still lecture 18, slide 10. So all I need, if I want to calculate free fall acceleration on the surface of the sun, all I need is the mass of the sun, which is given in the problem, the radius of the sun, also in the problem. So all you need to do, just plug numbers in, and then calculate the free fall acceleration on the surface of the sun. All right? Try this. Okay, so if you plug all the numbers in, the acceleration, free fall acceleration on the surface of the sun is going to be 275 meters per second squared. So it's definitely larger than the free fall acceleration on the surface of the Earth. So if you ever go to the sun, well, you probably don't want to do that because it's too hot there, right? But if you get close to the sun, you should be prepared. You're going to feel heavier and heavier, okay? It's because the gravity of the sun is much stronger than the gravity of the Earth. So you feel a larger free fall acceleration. So the weight you feel is going to be greater, okay? So this is a general conclusion for any star or planet. If you want to calculate the free fall acceleration on the surface of the planet or star, Now, what if we want to find out the free fall acceleration at a point above the surface, right? So, not like 10 meters above the surface, right? 10 meters above the surface, it doesn't make any difference, right? Like a few hundred kilometers, okay? Say there's an object, this is still the Earth. Now the object is very high above the surface of the Earth. And then I still want to calculate the free fall acceleration of this object. I would still do this, right? I would still use the general equation and then plug in the mass of the object, the mass of the Earth, and then now the radius, the distance I plug in is still going to be, because you can't ignore the size of the Earth, you can plug in the distance from the end center of the Earth to where the object is. So this is going to be the little r you plug in, okay? You see that little r is the distance. It's not always the radius from the problem, okay? So I'm going to plug in this little r squared, and then you can still factor out this little m. Then you would just get this factor. And now this factor is going to be the little g at that point, right? So, okay, so now all I need to do is this. So this is going to be a general conclusion. Let's put little r here. So for any point, doesn't matter if it's on the surface or above the surface. If I want to calculate the free fall acceleration, I would just do this. Big G times the mass of planet or star divided by this little r, with this little r, the distance from center to where the object is, right? If the object is on the surface, this little r is going to become the radius of the planet or star. If it's not, then you can see that it's going to be the radius of the planet or star plus the height of this object, right? So if you tell me this object is like a few hundred kilometers above the surface, this is going to be the little r, the distance I plug in, right? Little r is not always radius, okay? All right, so a lot of people, they get confused by little r and big R and this part. You need to understand what they mean. Little r comes from this equation, and this is always the distance between these two objects. When we talk about an object and a planet or star, because the planet and star are very huge, you can't ignore the size and treat them as point masses. So you're going to use the distance from the center of the planet or star to the object. So that's the little r, right? That's the distance. What is big R? We usually use big R for the radius of a planet or star because they are usually big numbers, right? So we use big R for them. Okay. Sometimes little r will become big R in a problem. Say if I just work on the surface of planet or star, right? Little r is still the distance, but now the distance becomes the radius of planet or star, because I just need the distance from center to where the object is. If the object is on the surface, of course the distance will be equal to the radius of the planet or star. Okay? Once you understand the difference between these symbols, where they are confusing. Whenever people see little r, big R, they will just read it radius. Okay? But in this case, this little r here, it's always a distance. Is it going to be big R? Well, draw this diagram, then you know what little r is. What's the connection between little r and then big R? So that means this is going to be a general conclusion, right? I don't need to use big R or anything like that. All you need to do, just find out the distance from the center of the planet or star to where the object is. Then plug it in, right? How do you find this little r? That's how you find the little r, right? Okay? So this is a general conclusion for any point, right? Now again, I want you to practice the conclusion. This is more general, right? So take a look at slide 12. A space shuttle orbits 350 kilometers. You see kilometers, right? You should watch these units yourself. No one is going to remind you about these units on the test. Okay? Above the surface of the Earth, what is the free fall acceleration inside the space shuttle? Okay, now the space shuttle is really, really far away from the surface, right? It's not like only 10 meters from the surface. Then the free fall acceleration is still going to be 9.8, right? It doesn't make any difference. Now the problem tells you it's 350 kilometers above the surface, so it's actually telling you this distance, right? But if I want to use this general conclusion to calculate the free fall acceleration inside the space shuttle, I need to use this total distance. But this total distance is going to be the radius of the Earth plus the height of the object. If the problem only tells you the height of this object, okay? And then you just plug in. But so the mass of the Earth is given, the radius of the Earth is given. Remember, convert the height to meters. All right, so that's the R you're going to plug in. That's the only difference, okay? And then, again, pause the video, do the math yourself, see if you can get the same answer I get. All right, so in this case, you will get 8.83 meters per second square, okay? So it's definitely smaller than 9.8 because it's very far away from the surface of the Earth. The free fall acceleration is smaller, so people inside the space shuttle is going to feel a little bit lighter than usual, okay? And that's why if they're very far away from the Earth, if you have seen these astronauts, they're almost floating in the space shuttle because they feel almost weightless, okay? Because they're really far away from the Earth. This number becomes really, really large, so the G almost 0, okay? All right, so that's the little g. Again, it's a conclusion from the general equation. This is not something I need memorize. We will see a lot of conclusion in this part, but everything can be derived from this general, fundamental theory. Now we're going to talk about satellites, okay? Slide 13, okay? Because we know there are a lot of satellites orbiting the man-made satellites orbiting the Earth, right? So these satellites, they're orbiting. So let's use this guy as the cell. They're orbiting in this around the Earth in almost a perfect circle. Not a perfect circle, but for simplicity, we're just gonna assume it's a perfect circle. So we can just use the theories we learned to study the orbits of these satellites. And we're gonna draw two very interesting conclusions for satellites. Okay, so let's see. The first thing we want to find, the first thing we want to figure out is the velocity of the satellite, okay? So how do I find the expression for the velocity of these satellites? Now these satellites, remember, now they're in a circular motion, right? Because they're orbiting the Earth. If they're in a circular motion, there must be a centrifugal force toward the center, right? Always. That's a theory for circular motion. That's true for any objects in circular motion, even for satellites, right? Even for Earth, okay? So that means when this guy is at any point, there must be a force toward the center. And which force is the centrifugal force in this case? The gravity from the Earth on the satellite, right? So in this case, gravity is the centrifugal force. So that means if I calculate centrifugal force using the centrifugal force equation, and I calculate the gravity from the Earth on the satellite using this equation, I should get the same numbers, right? I should get the same number. Now, let's do this. Let's set them up. So, in this case, gravity equals centrifugal force, right? Because gravity is the centrifugal force, in this case, for these satellites. Now, I'm going to plug in use the gravity equation we just learned. The mass of the satellite, I'm just going to call it little m. The mass of the Earth, I'm just going to get big M, divided by, now it's going to be little r, right? Because it's not orbiting on the surface, right? It's usually very high from the surface. Now, okay, so this number should be equal to the number if you use a centrifugal force equation, mv squared over r. Now you see that you can rearrange this equation to find an expression for v. We want to find a general expression for v. Okay, the speed of the satellites in orbit. Okay, of course, at the end, I'm going to plug in r equals big R plus h, right? Okay, but now when I rearrange this equation, I will just rearrange that with a little r. Okay, so that's the question on slide 14. I want you to rearrange this equation, find the v, find the speed of the satellite for me. Okay. All right. So let's see. When I rearrange this equation, I should be careful. Okay. I don't like denominators. Every time I see denominators, I want to get rid of them. Right. Either you cross multiply, or you just multiply both sides by the denominators. Right. In this case, because this is r squared, this is r, so let's multiply both sides by r squared. So that's gonna get rid of both denominators. Right. On the left hand side, I will get g m m. This cancels that, or r squared. So on the right hand side, I will get m v squared times r. Right. So I still have one power of r left. Now it's easy. If I want to find a v, I first divide both sides by m and r. What do I get? I would get g big M, that's the mass of the Earth, right? Divided by r, because this m and m cancel. Now this m and this m, they're going to cancel as well. So, and this r and this r, they're going to cancel. So I will get v squared. And then just take a square root on both sides, right? So at the end, you will get an expression for the v like this, right? And then if you want to replace this little r with this r plus h, that's fine, right? But I know this little r is not always the radius of the Earth or anything. It's always a distance from the center of the Earth to where the object is. So which one is going to be the right answer? That's going to be B. B is the right answer, okay? Because the little r, it's going to be equal to r plus h. Okay? So, and then this is the conclusion for the speed. So that's the first conclusion we wanted to draw. Now the second conclusion I want you to draw is this. Slide 15. Can you also find an expression for the period of the satellite? Okay, I just found v. Is there a way I can connect the period and v for the satellite? Yes, we can, because okay, the satellite is in a uniform circular motion. In a uniform circular motion, you can always do something like this. You can always connect the v with the period and the radius. Okay, how do we connect them? We connect them by using, if you still remember this, by using the definition of speed. Speed is always distance divided by time, right? Always. Now, in a circular motion, it's moving in a circle, but I can still do this. So I'm going to pick the period as the time, a very special time. If I pick the period and then I still want to calculate the velocity, I will use the distance it travels in one period, which is the circumference, right? So I would have 2 pi r at the top. All right, so in this case, now you see that I have found a connection between v and t. And I just found t, I just found v. So if I rearrange this equation, I will find an expression for period. Okay, so that's what I want you to do. You're going to plug that in here, right? And then, rearrange this equation a little bit and see if you can find the final answer, a simplified expression. And at the end, I can replace little r with this, right? But when I rearrange this equation, I'm just going to carry little r. I'm just going to keep in mind little r is always the distance from the center to the where the satellite is. Okay, so this algebra is going to take you some time because you're going to divide this by this. Okay, All right, so I want you again, pause the video, do the algebra yourself, see if you can find the right answer. Now, okay, I'm going to do that now. T equals 2 pi r divided by this whole thing. Okay, this is really confusing. I have a square root, and there's a fraction under the square root. How do I divide these two things so that I can get the simplified expression? Let's do this. So let's first multiply both sides by this, okay? Because I don't like denominators, right? Denominators are always confusing. So if you multiply both sides by this denominator, you would just get t times this, right, equals 2 pi r. Okay, that's much nicer than this, okay? At the end, we're gonna get rid of, we're gonna divide things, okay? But now, I don't like square roots, right? I want to get rid of square roots, right? If I want to divide things by square roots, that's confusing. Just square both sides. If I square both sides, what do I get? I get t squared g m r, so that gets rid of the square root. Now the right hand side we get 4 pi squared r squared. I'm going to square each of them, right? Now you can divide, right? So again, when I have denominators, I will be very careful. So what I do is that I'm just going to multiply both sides by the denominator first. Doesn't matter what I want to do next, because I don't like denominators. They're always confusing. So if you multiply both sides by r, you would get t squared times gm. Okay, much nicer on the left hand side. On the right hand side, you get 4 pi squared r cubed. Now you see that you can just divide, right? You don't have denominators, you don't have square roots. Very nice. T squared equals 4 pi squared r cubed divided by big GM. Now just take a square root. Okay? So these are the two conclusions we drew, right? So I'm going to list them here. For any satellite, the speed is always this. And the period, okay, well, it's going to be a complicated expression, but that's fine. Okay, so I've summarized these two conclusions on slide 16. And then, of course, I'm going to erase this. Of course, if you want to plug in the height, you will get this. The little r is not always the radius. Well, in this case, it's the radius of the circular motion. Yeah, you can say it's still the radius, but it's not the radius of the Earth, right? Plus the height of the satellite. And then this is going to be 4 pi squared r, the radius of the Earth, plus the height of the satellite cubed divided by gm. And then you can see that the speed and period, both of them don't depend on anything other than radius or the height, right? So any satellites in the same orbit, they will always have the same r or the same h, right? So they will always have the same speed and period, okay? And that makes sure that these satellites, when they are in the same orbit, they're not going to collide with each other. Right. This was a problem. This was something that bothered me when I was a kid. If there are so many satellites there, how do we make sure there's no traffic there? There won't be any traffic there, right? Any two satellites, if they are in the same orbit, they always orbit the Earth with the same speed, the same period. They're not going to collide with each other. They're not going to catch up with each other. The distance between them is still always going to be the same, because they always orbit with the same speed, the same period, right? And that's a conclusion from this theory, Okay? You see that physics is everywhere. It's everywhere. So you don't need to worry about these satellites. Once you launch them in the orbit, just let the satellite orbit. It's not going to collide with other satellites. Okay? Because the period and speed depend only on where the satellite is. It doesn't depend on the mass of the satellite, the size of the satellite, what it's made of. It's just going to orbit there because of gravity. All right? These two conclusions, they're conclusions from this law. Okay? So these two equations, you need to know how to derive them. You need to know how to derive them. They're not going to be given on the test, okay? Again, you don't need to memorize that, especially this one. I can't remember this one, okay? And there's no point doing that, okay, in physics, okay? All you need to know is that, how did we derive these two equations? The first thing we did was this. Because gravity is the centrifugal force, when I equal them, I will find an expression for V. Right? So that's how we found this guy, okay? And then once you find a V, how do you find the period? Well, think about it. I'm gonna still use the definition of speed in a circular motion. If I do distance over time in one period, I will do circumference divided by period. Okay, circumference is 2 pi r. And then you use this equation. You do some algebra. This algebra is a little bit harder than this, but still do everything carefully. Don't skip steps, okay? Rearrange this equation, you will get an expression for T, okay? That's what we're learning in physics. We're not learning how to memorize all these conclusions, okay? All right? So that's it. You need to know how to derive these two equations. Now we can apply them. Now let's apply them. Say I have already derived these two equations. Now I'm going to apply that to the question on slide 17. The question on slide 17, the International Space Station is orbiting at an altitude of about 320 kilometers above the Earth's surface. What is the period of the International Space Station? Okay. If I want to find the period of the space station, well, we just derived this equation. So all I need to do is that find all the numbers and then plug them in. It's orbiting the Earth, so mass is going to be the Earth, right? Big G constant, 4 pi constant, radius of the Earth constant. So all you need is the height of the satellite. In this case, it's the space station, and the height is 320 kilometers. Okay. So the height is going to be 320 times 10 to the third meters. Plug this number in, do this algebra carefully. That's when a lot of people make mistakes, okay? There's a cube, square, they forget, and the square root, they forget, okay? What I would do is this. Add these two numbers together, enter. Cube that number, enter. Leave it there. Then do this number times 4, enter. This number times pi squared, enter. Leave it there. Calculate G times M, enter. Pick these two numbers from a calculator, divide them, enter. Take a square root. I do everything in steps. I'm not going to enter all the numbers once and then enter. Most likely you're going to make a mistake, especially if you have an equation like this, you want to plug numbers in, okay? Do things in steps, even for plugging numbers in your calculator, okay? Make sure you get all the numbers right, okay? So I want you to do this algebra as a practice, okay? Plug all the numbers in carefully. At the end, you will find the period I found. What is the right answer? B. Okay, did you get the right answer? All right. So and then of course it's going to be in seconds. If everything is in SI units, the final answer will be in SI units. In this case, it's a time. It's still going to be seconds. All right. All right. So that's this. Now, okay. If this is true for any man-made satellite, it must also be true for natural satellites. and there is a natural satellite orbiting the Earth, which is the moon. Okay? So that means I can also apply this conclusion to the moon. Okay? So that's what we're going to do in the next slide, slide 18. Okay, now I'm going to apply this conclusion to the moon. Let's read this problem. The average distance from the center of the moon to the center of the Earth is this number, kilometers. What is the moon's period around the Earth? Okay. The moon is a satellite orbiting the Earth. Okay, I'm just going to go ahead and use this period equation. So let's see. And the only number I need is going to be the r, or this h. Now what's happening here? So if this is the Earth, this is the moon is orbiting the Earth, right? So the problem already tells you the distance between these two centers. So it's already telling you the r. You don't need to add anything, right? It's telling you the distance between the center of the Earth and the center of the moon. That's already the r between these two objects. So you just go ahead and plug it in. Again, the r is in kilometers. Okay, so you're going to plug in, convert it to meters first before you do the algebra. Okay, now just put it in here, constant, and then which mass do you use? The mass of the moon or mass of the Earth? The mass of the Earth, right? When you use these two equations, the big M is the mass of the planar star at the center, not moving, not the mass of the object orbiting them, right? When we did the algebra, actually the little m cancel out, right? The little m, which is the orbiting object, cancel out. You don't need them. Okay. All right. So plug them in. Okay. Use your calculator, as I said. Do the algebra in steps. Don't put all the numbers in and then enter. Calculate each term. Enter. At the end, square root. Enter. Okay. All right. Did you get the right answer? What is the period for the moon? That's A. Okay. Again, it's going to be in seconds, right? So that's the moon's period in seconds. Now, I want you to convert this to days for me. How many days is this? Okay, because this is in seconds, right? I want you to convert to days. So how do I convert it to days? Well, all I need to do is that 1 day is going to be equal to how many seconds? What's the conversion? 24 hours, each hour has 60 minutes, each minute has 60 seconds, right? That's a conversion between a day and seconds. Plug the number in. What is the number you got? So it's about 27 days. Okay, it's about 27 days. Did you get the right answer? Okay, that's the definition of a lunar month. Take a look at the slide, the last slide. A lunar month is the time between two full moons, okay? So, and then that's the period of the moon orbiting the Earth. So you can take a look at this, the definition of lunar month, okay? And there are different, there's some slight difference between these definitions. You don't need to worry about these the fancy names there. I don't even know what they mean, okay? But you can see the numbers on the right, okay, listed on the right. The length in days for lunar month, it's always about 27 days, right? That's because the period of the moon orbiting the Earth is about 27 days, okay? And this is definitely shorter than a month in Gregorian calendar, right? In Gregorian calendar, usually it's like 30 or 31 days, or like for February, it's like 28 or 29, but it's longer than that. So the dates on the lunar calendar don't overlap with the dates on Gregorian calendar, right? And then if you know that we use the lunar calendar in China, well, we use both, but the Chinese New Year, if you heard about it, if you know about it, it's always the January 1st on the lunar calendar. It's not the January 1st on Gregorian calendar, right? So usually it's gonna be late January or early February on the Gregorian calendar because of the difference between the lunar month and the month in Gregorian calendar. Okay? So this is the cell light. Okay, when you see cell light, first of all you need to know how to derive these two equations, and then when you see a cell light, it's always most likely it's going to be these two equations. Okay, you derive these two equations and you plug numbers in, and then play with these two equations. Okay, because these are the conclusions we drew only for cell lights, right? Only for cell lights. Okay. All right, now we're going to move on to the next slide. We're going to revisit gravitational potential energy. Well, you would say, why do we want to do that? Because we already learned gravitational potential energy. What is the equation we learned for gravitational potential energy? Okay, that's that equation. Right, I'm going to erase this. UG mgh, right? So, but there's a problem. If you want to use this equation for like satellites or even the moon or anything like orbiting the Earth or even flying away from Earth, they still have potential energy, right? They still, like the moon and the satellites, they're still orbiting the Earth. They still have potential energy. But if you want to use this equation, there's a problem. What is the problem? Think about it. What is the problem if I want to use this equation for a satellite really far away from the Earth? Or the moon, also really far away from the Earth, okay? Anything orbiting the Earth with a very large distance. What is the problem? What is the problem? The problem is this little g, right? Because we just learned that little g, well, it's 9.8 on the surface of the Earth. Yeah, that's true. But what if it's like a few hundred kilometers away, right? We have seen that. We just calculate, we just solved the problem, right? It's going to get smaller and smaller. So if you talk about this object very far away from the Earth, but still orbiting the Earth, then you want to use energy method. This equation is not going to work because this little g is going to change. It's not going to even be a constant, right? This is the conclusion we draw. It depends on the distance from the object to the center of the Earth, right? And of course, if the distance changes, the little r changes, right? Assuming it's really far away, the height is comparable to the radius of the Earth, right? If this guy is only like moving very close to the surface, only 10 or 20 minutes, you can still use that equation, right? But if for something like this, right, take a look at that image on lecture 19, slide 1. Okay, this object is still moving around Earth, but the distance is really far away. The little g is changing all the time, right? If it's changing all the time, this is not going to work. Okay, this is not going to work. So we'll need to find a new equation for this gravitational energy. If I want to use energy method to make predictions for these like satellites and anything orbiting the Earth at a very far distance. So that's why we want to revisit gravitational potential. This guy is not going to work because the g is not going to be a constant. Okay. Now, but you can use the fundamental theory. There is a fundamental theory in physics. Take a look at the equations and on slide 1. Okay, it's a little bit scary. The potential energy is always defined as the integral of the force, okay, over the displacement, okay, and with the negative sign. All right, so that's the fundamental theory in physics. So for any force, if it's conservative, if you remember the theory we learned earlier, you can always define potential energy associated with this force. Gravity is a conservative force. That's why we can define a potential energy. Okay, and then if you use that theory, okay, now you plug in the force equation, the general equation of the force. In that theory, at the end, you will get a new, more precise equation for the gravitational potential energy we're going to list it here. So I'm not going to use this equation anymore because this doesn't work. The new equation, it's going to be this. Okay? What is big G? Big G is a constant. Big M, the mass of the Earth, or any planet or star you want to discuss, right, in the problem. The little m is the mass of this orbiting object, okay? And the little r, again, it's gonna be the distance from the center of the Earth to where the object is, okay? So at the negative sign is totally convention. It totally comes from the theory, because there is a negative sign in that theory, right, the first equation. Again, you don't need to worry about how to derive this equation, okay? So this equation will be given, okay? This equation is going to be given, okay? And this will be given. This is the fundamental theory. But again, then this theory, a lot of people already remember that. This is also a very famous equation. This equation is going to be given, but the rest, no. They're just conclusions from this theory, right? This is also a conclusion, but we don't need to know how to derive that, okay? All right, so then that's going to be the equation we use to solve any problem using energy method. This R, remember, is the distance from the center of the Earth to the object, right? So be careful, it's not always the radius of the Earth, okay? And don't forget the negative sign, okay? A lot of people, they're afraid of negative sign. Don't drop it. Okay. Then what is the connection between this equation and that equation? Actually, you can show that on slide 2. When you apply this equation on the surface of the Earth, very close to the surface of Earth, you subtract these two terms, you see that you're plugging RF. Now you're going to plug in RF and RI, right? Because the only thing that changes in this equation is going to be this distance. Big M, little m is not going to change for the same object. You want to apply, you want to do energy on the same object. This guy is going to change. So you will have RF and RI, and then you do the math. And then because when it's very close to the surface, you will have RI and RF very close to the radius of the Earth, right? You use that approximation. At the end, you see, you will get the energy is almost mg. The change is going to be mg final height minus initial height. Okay? So on the surface, this equation will reduce to that equation we have been using. So there's no problem. Okay? There's no contradiction. Okay, there's no contradiction. This is just a simple version of this equation when we discuss things just very close to the surface of the Earth. Okay, but if something is really far away, if you still use this equation, first of all, you don't know what the g is. Secondly, the g is even changing, okay, all the time. So you will need to use this equation. And in this equation, the only variable is going to be the distance. And distance is very easy to measure, okay? So that's going to be the equation we're going to be using in this part. Okay? So in this part, when you use energy, right? Take a look at slide 3. When you use energy and you want to calculate kinetic energy, potential energy, kinetic energy is still 1/2 mv squared. That doesn't change, okay? Gravitational potential energy is because this is only an approximation of this real equation when it's very close to the Earth. So when something is very far from the Earth, we have to use the real equation. There's nothing wrong with this equation. This is a very good approximation on the surface of the Earth. But when something is very far away, we're going to use this equation, okay? Then you can still use conservation of energy, right? The total energy in the system, the change in the total energy of the system equals the external work, okay? And then the total energy is going to be kinetic energy plus potential energy, and the potential energy will have a negative sign. Keep the negative sign. Don't drop this negative sign. Potential energy can be negative. Potential energy is relative. It totally depends on where you call 0. Even if you use mgh, right? What is the height defined, right? What if you are on the 10th floor, you do experiment? What is the height? Which is your 0 reference, right? You use the floor on the 10th floor or use the ground. There's nothing wrong. You can use either one, right? You will get the same answer. But if you pick a 0 reference, anything lower than that, you will get a negative energy, okay? Potential energy, that's fine, okay? So we'll see some examples next time. I'm going to stop here for this video.